next speaker is Alexander Cohen, who is a junior specialist with the Deep Space Group at UC Santa Barbara. He received in 2019 BS in physics and a minor in astronomy and planetary science from the university. And his specializations include CAD and finite element analysis, and he has been working with collaborators from the academia and national labs to develop a model of damage due to gas accumulation within a relativistic spacecraft traveling through the interstellar medium. So let's welcome our speaker.
Thank you very much. Hope you're all doing okay with the cold. It looks like we're getting some sunlight now. So we're going to change gear a little bit and talk about some issues that a spacecraft such as those proposed by the NASA Starlight program and the Breakthrough Starshot program could experience when traveling through the interstellar medium. So we're going to talk about impacts with the diffuse gas that exists between the stars, as well as the deleterious phenomenon that can occur post-impact. So, of course, if exploration beyond the outer limits of the solar system is to be achieved within reasonable fractions of a human lifetime, we need a radical shift in propulsion technology. Now, as we've heard and are all probably pretty familiar with, the NASA Starlight program proposes that you use directed energy propulsion upon a low-mass spacecraft. We propose a 1 to 10 kilometer aperture and a 100 gigawatt class laser phased array. With a 1 gram spacecraft, this system has the ability to accelerate the spacecraft to approximately 20–25% the speed of light, and can enable exploration of nearest star systems within 20 years. So this graph kind of shows a this graph kind of shows the technological divide that exists in propulsion, where in the bottom right you see how we have achieved highly non-relativistic propulsion with chemical acceleration, and then in the top left you see highly relativistic electromagnetic acceleration of particles and things like particle accelerators. And this huge technological divide is what we are trying to achieve with directed energy propulsion. So let's talk about the interstellar medium and its composition and homogeneity. So the interstellar medium is composed of roughly 99% gaseous matter and approximately 1% granular dust by mass. Of the gaseous matter, approximately 70% is hydrogen, 28% is helium, and 2% is heavier elements such as carbon, oxygen, and iron, among others. As well as consisting of gaseous matter, you also have dust. You have hydrocarbons, silicates, and ices. They're usually crystalline or amorphous grains of sizes less than 1 micron, and we're going to hear more about these phenomena later. So on scales from 10 to 100 light years, the interstellar medium is highly inhomogeneous. There are regions of higher and lower density, as well as regions of interaction with stellar winds, where you can get much higher temperatures and pressures. However, for local targets like Alpha Centauri, we can approximate the interstellar medium as a homogeneous gas of atomic hydrogen with a density of approximately 1 per cubic centimeter and a temperature of approximately 8,000 degrees Kelvin. So let's talk about some relativistic spacecraft design. So in the baseline system proposed by the NASA Starlight program, you have a single, extremely thin, approximately 100 micron thin semiconductor wafer or hybrid disk of size approximately 25 to 100 millimeters. The wafer will house the entire spacecraft system, such as the bus, the sensor suite, the power system, and the communication system. The lowest mass missions have a wafer and reflector mass of order 1 gram, although since we use a modular and entirely scalable propulsion system, it's capable of larger mass missions with speed scaling as m to the -1/4. A thin-walled plasma-etched honeycomb pattern on the backside of the wafer reduces the overall mass, and it also enhances the structural integrity. And of course, the spacecraft would fly edge-on to reduce the impact cross-section. So let's talk about some instantaneous ion-matter interactions. So this is a schematic of some of the basic phenomenon we expect to see when impacting a diffuse gas at a quarter the speed of light. You'll get hydrogen and helium implantation below the surface. You'll get heavier species impacts, such as carbon and oxygen and iron, and you'll also get secondary particle production upon impact of these particles, such as neutron production. You'll also get bremsstrahlung, X-ray, and gamma-ray production. Of course, the hydrogen and helium will lose almost instantly, will lose their electrons, and so we can approximate the ISM as a fully ionized constant velocity beam in the spacecraft frame. The ion-matter interactions will include sputtering, displacement of target atoms, thermal spikes, and implantation. So the analytic Bodansky and semi-empirical Yamamura formulas are appropriate tools to discuss things such as sputtering and material erosion in a spacecraft like this. In this expression here, we have the depth of material eroded as predicted from the semi-empirical Yamamura formula. Phi is the fluence of the incident species. Fluence is the integrated flux, so it's the total amount of impacts per unit area over the entire duration of emission. Y is the sputtering yield. M2 is the atomic mass of the target material, and M1 is and rho 2 is the mass of the mass density of the target material. So this graph shows total erosion as predicted by this semi-empirical Yamamura formula. You can see that for silicon and copper, for journeys to Alpha Centauri with speeds between 0.1 and 0.5 c, that the erosion is less than a single atomic layer. And this is the case because energy transfer during collisions between highly energetic light ions and heavy atoms is inefficient, as well as because the energy transfer occurs deep below the surface where the nuclear stopping cross-section becomes comparable to the electronic stopping cross-section. This shows the same thing just for silicon and copper. Sorry, this shows the sputtering yield. So this is a schematic of some of the various bubble formation phenomenon that we expect to see. Bubble formation, blistering, and exfoliation are all deleterious phenomenon that are caused by the accumulation of relatively insoluble gas atoms below the surface of a target. The bubbles the implanted material, once implanted, can aggregate and form bubbles which have certain transport behavior, and if they reach a critical concentration, they can change the surface morphology and burst at the surface. Each A, B, C, and D show the various phenomena that can occur as a function of the fluence. At low fluences, individual gas atoms are just implanted in the material and they stay trapped in the lattice vacancies. At low fluence, about 10 to the 18 impacts per meter squared, you get nanoscale bubbles forming, but they don't aggregate and they produce no visible surface effects. In the intermediate fluence range, between 10 to the 18 and 10 to the 21 impacts per meter squared, the local gas concentration can put stresses on the material, and you will begin to see morphological changes at the surface of your spacecraft shield. And at higher fluences, greater than 10 to the 21 impacts per meter squared, the surface blisters can begin to burst, and you can get things like exfoliation, flaking, and material erosion of the surface, which is shown in D. So we can discuss bubble formation further. If we just consider beta block stopping, so just electronic stopping, you get this prefactor in front of the beta block stopping formula where Z1 is the atomic number of the incident ion and Z2 is the atomic number of the target material. This predicts that helium will have a stopping power approximately 4 times larger than hydrogen. However, since the mass of helium is approximately 4 times the mass of hydrogen, helium will have approximately 4 times more kinetic energy and thus will implant at a similar range as hydrogen. These are some figures which show what these phenomenon look like on your right, I guess. You see gold sample after irradiation of from helium ions at 4 keV, and you see the bubble formation below the surface. And this is actually at a fluence which is comparable to what we expect to see. And then the diagram on the other side shows damage in the intermediate fluence range, and you can see blister formation and exfoliation and bursting at the surface as well. So there are 2 kind of cases that we can discuss. Most of the literature in the bubble formation is done in beamed experiment cases where you have a target which is much larger in general than your beam size. Now this leads to a distant, so the material will implant itself below the surface at a distance which is comparable to the range, the distance to the nearest surface from the implanted species is comparable to the range of the implantation distribution because the closest surface is the surface of impact. Whereas in a thin spacecraft, the distance to the nearest surface is basically 0 since you have a thin target and the beam spans the entire forward-facing cross-section of the spacecraft. So we expect to see bubble formation and morphological surface changes at the surfaces with normal vectors perpendicular to the incoming flux. A simple theoretical model of blistering onset was produced by Martinenko back in 1977. The local pressurization is determined from the concentration of dissolved gas atoms, C sub G, and the dissolution energy of the gas species in the target material. Now, there are two expressions for the gas concentration. One is just phi over delta R, where you don't take into account diffusion in the material, and then if you'd like to include diffusion, you can include this extra term in the denominator in the radical, where D is the diffusion coefficient and T is the irradiation time. However, it is often assumed that irradiation damage produces enough defects in the material that the defects can serve as trapping sites, and thus the diffusion coefficient can become negligible. However, you reach a critical concentration or a critical pressure when your pressure in the bubbles reaches the yield strength of your material. And at that point, it leads to bubbles bursting because the material will fail. So in order to find implantation distributions of ISM gas atoms at relativistic speeds, we use a Monte Carlo binary collision approximation code called SRIM. This predicts that at velocities greater than 10% of the speed of light, hydrogen and helium will impact at the same depth, as we just talked about with the beta block stopping. This leads to a mixed hydrogen, helium, and solid layer, which can lower the blistering threshold, since the transport behavior of materials of implanted gas below the surface is different. And for velocities greater than 7% of the speed of light, the helium implantation distribution fits entirely within the hydrogen implantation distribution, as shown here. So this is a plot of the depth of the implantation depth for different speeds, and you can see it's just normalized to 1 so that we can show what it looks like on the same scale. Okay, so in the spacecraft frame, the ISM hydrogen will impact with energies between 4.7 and 45.3 MeV, depending on the spacecraft beta, and the ISM helium, being more massive, will impact with energy between 18.8 and 180 MeV. And just for reference, at 20% the speed of light, the hydrogen will impact with a kinetic energy of 19 MeV, and the helium will impact with an energy of 45 MeV. So for this analysis, we assume an ISM number density of 1 per cubic centimeter, just for simplicity, and with hydrogen contributing 92% and helium contributing 8% by number, the resulting fluxes at 20% of the speed of light are 2.8 times 10 to the 13 per meter squared per second, and for hydrogen, and for helium, it's 2.4 times 10 to the 12 per second per meter squared. Of course, this is a function of the travel speed, whereas the fluence, the total integrated impacts, is independent of the travel speed. And for a 4.37 light-year journey, which is approximately the distance to Alpha Centauri, we expect to see fluences of order 3.8 times 10 to the 22 per meter squared for hydrogen and 3.3 times 10 to the 21 per meter squared for helium. Now, this plot shows the critical concentrations of implanted gas atoms for a range of dissolution energies. It assumes a constant ISM number density of 1 per cubic centimeter, and it suggests that materials with yield strengths in excess of 10 gigapascals will not blister. In general, it's difficult to appropriately determine the appropriate yield strength to mitigate blistering, because the standard yield strength greatly underestimates the critical fluence for many materials, and this is shown by the left black line at 250 megapascals. This is for copper. An alternative strategy, as also proposed by Martinenko, is to estimate the yield strength as 10% of the elastic modulus, which is the rightmost figure. However, it's important to note that this figure shows the critical gas concentration and thus the fluence threshold for blistering. However, bubble formation, swelling, and changes to the material properties are expected at many orders of magnitude lower fluence. In copper, the diffusion coefficient must exceed 10 to the negative 17 meters squared per second for classical diffusion to be significant. And diffusion is significant when the diffusion length becomes comparable to the straggle of the implantation distribution. This analysis, of course, assumes an isotropic diffusion coefficient for various gas species, but implanted atoms can behave differently because they have different transport behavior when other species are present, or if there are lattice defects in the target. For example, hydrogen-helium atoms in many materials aggregate and form bubbles, and the hydrogen and helium bubbles together have synergistic effects that can drive deleterious phenomenon further. Similarly, insoluble gas atoms may interact strongly with material defects, as I described before. So therefore, an understanding of hydrogen-helium interactions in a solid, interactions with material defects, defect production by irradiation, and interaction of near-surface gas atoms with material surfaces will be necessary to design materials resistant to bubble formation, cracking, and blistering. This figure is a schematic of some basic proposed circumferential shield designs. So for a disk-like spacecraft, we propose a circumferential shield, which must satisfy three main requisites. The first is that it must block any incoming proton radiation without structural failure due to bubble formation. The second is that it must stop any incoming heavier species, such as carbon, oxygen, or iron. It also must mitigate the production of secondary particles, such as neutrons and Bremsstrahlung X-rays. Therefore, an effective shield will likely be at least 2 times as thick as the hydrogen and helium Bragg peak is deep, where the Bragg peak is the implantation depth in a given material. If you look at the top right-most version, you have a sintered material. One proposed method is to have a sintered material that surrounds the Bragg peak. The sintered material has a granular nature with a characteristic grain and hole size, which makes it resistant to bubble formation. You can imagine that if a bubble forms within a grain, it will want to burst at the grain boundary rather than migrate to the surface and burst at the surface. So you can resist bubble formation that way. A similar method is to use a porous ceramic, which allows the storage of implanted gas atoms in its pores. This is shown in B. In C, we show a self-annealing metal, which can be induced from solid into liquid and back again. This enables trapped gas to not aggregate and form bubbles, and you can let it diffuse out. And then a similar scheme is a metal powder, which will act similarly to a sintered material with its grain and hole size, making it resistant to bubble formation. In terms of discussing specific materials, a layered scheme with an initial layer of either sintered, porous, or powdered carbon, followed by a layer of tungsten is promising for 2 reasons. One, because carbon has a high energy onset of neutron production upon impact of protons, and tungsten is an efficient Bremsstrahlung X-ray absorber. So we would like to test these things empirically as well, ideally in a beamline, and it will rely on an appropriate accelerator facility. The accelerator facility will have to have high flux such that 20 years of fluence can be simulated in hours, days, weeks, or months. Similarly, we would like the ability to defocus the beam such that the flux can span the entire forward-facing cross-section of the sample. Similarly, since we're looking for high fluxes, the temperature of the target will be a large problem, and so ideally we would have the ability to control the temperature of our target. Of course, diffusion depends greatly on the temperature of the target, so this will be an important aspect of an experiment. Additionally, it would be useful to implant hydrogen and helium simultaneously so we can observe the synergistic effects of implanting different species. We would also like to be able to perform material diagnostics on our samples after they have been irradiated, such as we would like to do transmission electron microscopy, atomic force microscopy of the exposed surfaces, and then you can also use those things to determine the diffusion coefficients of various materials or various incident species on certain target materials. So in conclusion, what we take from this study is that materials with yield strengths well in excess of 10 gigapascals will likely remain below the model predicts that gas concentrations will remain below the critical concentration for blistering. However, regardless of whether blistering itself occurs, the high fluence suggests that bubbles will form in whatever shield you make. Some strategies moving forward in designing a shield would be the ability to increase the diffusion coefficient either by heating or by a different material choice. This can thus decrease the local gas concentration and may prevent bubble formation and blistering altogether. A material choice that accommodates a large amount of trapped gas would also be useful, something that's granular and sintered. Amorphous materials or liquid metals would be useful to discuss or to look into further. And you can also optimize the geometry of your spacecraft to minimize the cross-sectional area. So a needle-like spacecraft would also be useful for this purpose. Similarly, a better determination of the local interstellar cloud densities is crucial for accurately determining the fluence that a spacecraft will have to endure. And the largest takeaway from all of this is that a relativistic spacecraft must have an appropriate mitigation strategy to survive a journey to Alpha Centauri or beyond. We would like to acknowledge our funding from NASA in the NIAC Phase 1 and Phase 2, as well as funding from other sources for our collaborators, and we also acknowledge support from the Breakthrough Foundation as part of the Starshot program. Thank you.
Interesting talk. I was just curious, you mentioned that there's something like 1% of the material is in the form of dust.
Right. Right.
Have you considered what will happen? Have you modeled what will happen?
So we will hear that extensively in the next talk.
Okay.
Yeah.
Interesting, and I don't think anybody's looked at this before, but you seem to have mostly neglected diffusion.
Right.
The experiments with ion implanters that typically are used to produce bubble formation take place over hours or perhaps a day of implantation. You were looking at the diffusion coefficient, but correctly you should be looking at the square root of the diffusion coefficient times time.
Interesting.
And the time it takes to get to a nearby star is on the order of 600 million seconds. So I'm not sure that the results from ion implantation experiments of hours or even tens of hours are really relevant. You really need over periods of hundreds of millions of seconds.
Yeah, absolutely.
So there will be a lot of diffusion over a period of time.
I also think it was an excellent talk, but I think that you greatly overestimated between the Sun and Alpha Centauri by at least a factor of 10. So
Sure.
I think done this look bad, which is good. And
So
not bad is the same.
So there was a recent study by I think it's Glockler and Geis, who just made a measurement of the local interstellar cloud densities, and you're right, it is much lower, and we choose 1 per cubic centimeter just as an easy thing to propagate through calculations. Yeah.
Yeah, you gave some along the same lines some very specific estimates of the density in interstellar space. For us non-astronomers, could you say a few words about how that information is measured or derived, and what assumptions are built into it, like homogeneity and so forth, and how accurate it may be or not be?
Sure. Yeah, it's a particularly difficult measurement, right? Because you can only measure along a column, and so that measuring the density as a function of the distance is particularly difficult. Now, I'm not particularly certain how they make these measurements, but it is difficult for that specific reason, that you can't tell specifically where the densities are increasing or decreasing. You just get a column density along a column of a specific length. Correct. Right. Yes.
Yeah, I was wondering if, to kind of deal with Jeff's question about the time, if there's a database out there in terms of the medical proton accelerators, which are operating for very long periods. Right. It'll be the wrong parameters, but maybe give you some insight into how to scale those for longer time.
Certainly. In fact, most of the facilities we're looking at for beamline experiments are medical proton accelerator facilities. I'm sorry, can you repeat that one more time? Sorry. Oh, certainly. And well, the biggest thing is that it's a particularly odd scenario in our case because it's a low flux, high fluence situation, which is really difficult to experimentally verify, right? Because, so it's difficult because you either have to artificially increase the flux to correctly simulate the fluence, or you have to put something in a beamline for an extremely extensive period of time. So yeah, it's difficult. But there doesn't exist data that is particularly pertinent to this case. Yeah.
I was intrigued by your mention among your alternatives of, annealing the metal or liquefying it. I don't understand the mechanism by which in zero gravity that's supposed to get the bubbles to leave.
It's mostly to mitigate the formation of bubbles altogether.
Okay.
So you have a liquid so that the materials...
You're trying to take the defects out before
correct.
the bubble forms. Okay.
Exactly.
And more of a comment, and not just for you, but for the community. This issue you mentioned that we were just discussing about the lack of knowledge of the density of the interstellar medium is really a problem I want to foot stomp drawing the attention to. There are two different interstellar clouds between us and Alpha Centauri, the one that we're in and the one that we're not. And if there's any measurement worth its salt of the density of the one that we're not in, I haven't been able to find it. If anybody comes across that, will you please popularize it in the community? Because when you sit down to do engineering assumptions on these missions, the first thing you discover is the first number you need to know, we don't know.
Absolutely right. Yes.